In this video, we'll talk about what's called dependency preservation. This is another attribute that might make for a good thing to try to have in your good relations. Okay, so let's go back and talk about what a good decomposition is. Well, you want to eliminate anomalies, right? You want to make it so that it's very easy to edit your repository in a way that maintains the functional dependencies that you care about. Another thing is you want to have the recoverability of information. When you decompose into two parts, you want to be able to still recover all of the original information through lossless joins. One other attribute which we're going to talk about in this video is called the preservation of dependencies. Sometimes it's really useful to be able to check all of your functional dependencies, like to make sure they're all hold true, without needing to do a join. Once again, your functional dependencies are a lot like assertions or checks that say, my data should conform to this particular pattern. And you can always, if your data is in Boyce Codd normal form, you can always do all of the joins to build your original relation and check, does every functional dependency hold true? But sometimes joins are very expensive to do. Sometimes your table becomes huge when you have to join in all of this information and generate all this redundant data. Wouldn't it be nice if all of your subrelations made it possible for you to check all of your functional dependencies without having to do any joins? This is sometimes a useful characteristic. And once again, it's called the the preservation of dependencies. Okay, so how do we go about doing that? Well, if we want to decompose our relation into a form that preserves dependencies, this is something called normalization. The decomposition into Boyce Codd normal form is also called normalization. Normalization is when you turn a relation into a normal form. Okay, so we have a particular relation called R with a set of functional dependencies called F, and we want to break this into R sub 1, R sub 2, R sub n. We want to break this into subrelations. Okay. So what do we want to make sure we maintain? We want to make sure that we have a lossless join decomposition. Otherwise, we'd lose information, and this would be just a useless process. Once again, we're not trying to remove information. We're just trying to remove redundancy. Okay, now the other attribute that for now what we want to talk about is dependency preservation. So let F sub I be the set of dependencies in our closure of F that include only the attributes in R sub I. So it's basically, for this particular relation, check all of the functional dependencies that can be applied to R sub I. And now the rule is, if for all of the functional dependencies you can apply to each subrelation, if you combine all of those together, if you take the union of all of those together, you should be, and calculate the functional closure, that should be the same as the functional closure for all of them individually. It's basically saying, can you check that every functional dependency in each subrelation that you can use to test all possible functional dependencies that apply to this particular relation? Once again, that sounds really complicated, but it's really, for every functional dependency, is there a relation you can look at to check if that functional dependency holds? That's really the complicated way of saying the same thing. All right, so multiple choice question time. So what we have here is our original subrelation R, which is A, B, and C, and we have two functional dependencies. A functionally determines B, B functionally determines C. If we were trying to turn this into a decomposition, now there are two possible things we might want to look at. Here we have decomposition number 1, the decomposition on the left here, which is breaking into two subrelations, A and B and B and C. But another decomposition here is A and B and A and C. So the multiple choice question here is, are both of these two different decompositions in Boyce Codd normal form? All right, so let's talk about, once again, what is Boyce Codd normal form? It means that when you look at each subrelation, the functional dependencies that apply to it, the left side should be superkeys for that relation. So let's look here at R1 right here. We have A and B. Which functional dependencies apply to this guy? Well, A functionally determines B. So is A a superkey for this relation? Yes. Okay, so this one's in Boyce Codd normal form. What about this one? This one's B and C. Well, which functional dependencies apply to this guy? Well, B functionally determines C. Is B a superkey for this relation? Yes. So is R1 and R2, are both of these in Boyce Codd normal form? Yes. So is this a valid Boyce Codd normal form decomposition? Yes. Okay, this guy. Well, we already said that A and B is a valid Boyce-Codd normal form decomposition. What about this guy? Are there any functional dependencies that apply to this guy? Well, actually, if you go through and you go A to B and B to C, then there is a implied functional dependency that A functionally determines C. And is A a superkey for this relation? Yes. So is this relation also in Boyce-Codd normal form? Yes. So is this a valid Boyce-Codd normal form decomposition? Yes. So the correct answer here is yes. All of the subrelations are in Boyce-Codd normal form. Though this last answer, B to C isn't preserved, is also true. There's no way in this decomposition to tell whether or not the fact that B functionally determines C is true by looking at this relation or at this relation. You'd have to join them to do that. So decomposition 2 here is not dependency preserving. All right, I'm going to talk about that in more detail here. So when we decompose this relation into two forms, we can do this one, and we can say, okay, both R1 and R2 are lossless decompositions. But when we want to check for dependency preserving, what we need to do is we go, okay, the intersection of R1 and R2 is B, and B functionally determines BC. So this guy is indeed dependency preserving because I can check A to B with this guy, and I can check B to C with this guy. However, this guy is a problem. Okay, so once again, this is still a lossless joint decomposition. This is a valid Boyce-Codd normal form decomposition. However, when I take the intersection of R2, which is A, and then I try to go from A to AB, I can do that. But however, I can't check B to C without computing the join of R1 and R2 because none of our relations have B to and C in the same relation. All right, so how do you go about more systematically testing for dependency preservation? Well, the way that you go about doing that is you need to check each dependency. Here, alpha functionally determines beta. You need to check, is this preserved in our decomposition? So the way that we do this is we use a test that cares about the attribute set closure done with regard to F. So what do we do? Well, we start with saying, okay, our result is equal to alpha is equal to the left side. And then while we find new things to add to result, what we do is for each relation in the decomposition, we find the intersection between our current values, the current attribute set that we found so far, and the values in that particular relation. We take the attribute set closure of that, and then we take the intersection of that with R sub I. And then the next thing that we do is we say, okay, we add the things that we've calculated to our result. If the result contains all of the attributes in beta, then our functional dependency is preserved, that we can check this functional dependency somewhere. All right. So what we do is we apply this test to all of the dependencies in F and to check if the decomposition is dependency preserving. And this is a really nice algorithm because it takes just polynomial time that you go through and you don't have to calculate every possible combination of attribute set closures. All you need to do is you go through and you're always just adding things to result until there's nothing more to add, which is a lot easier to calculate than to calculate the full attribute set closure of all of your individual functional dependencies that you can maintain and make sure that that's the same as your functional dependencies that you start with without that limitation. All right, so let's go through another example here. We have anime traits here, which is name, hair color, tsundere status, eye size, and we have two functional dependencies. If you give me a character's name, I can tell you their hair color. If you give me their hair color, I can tell you their tsundere status. If I decompose this into hair, which has name and hair color, hothead, which has name and tsundere, and big-eyed, which has name and eye size, is this decomposition dependency preserving? All right, so let's go through this kind of piece by piece. So here we need to check in our decomposition. The first thing we would check is this a lossless join? But that's not really what the question is about. The question is just asking, is this dependency preserving? So what do? Well, we go and we start with, can we check that name functionally determines hair color in our decomposition? And the answer here is yes. We can look at the hair relation. And if you give me their name and hair color, I can check just by looking at this relation if this functional dependency is preserved. Now, what about this hair color to tsundere status? Can I look here to determine that? No. Can I look in hothead to determine that? No. Can I look in big-eyed to determine that? No. If I joined hair and hothead together, then I could check it, but unfortunately, with the way that we have this decomposition, there's no way for me to check if hair color functionally determines tsundere status in this decomposition. So the correct answer is here, no, hair color functionally determines tsundere is not preserved, and hence this is not a dependency preserving decomposition.